Hi my scholars, this is my school channel and my name is Abiola. Right here in this video lesson, we are going to walk through the subject chemistry for JAMB CBT past question the year 2010. Do not go anywhere, stay with us and we will be right back. Welcome back to my school YouTube channel, and in this video lesson we are going to attempt question 1 to 25. So let's begin with question 1. So which of the following is an example of a mixture? You know, for mixtures you can separate their components using physical methods, okay, like methods like your centrifugation. You know, when it even comes to examples like your blood, you know, you go to the hospital, they want to take samples, okay, from that particular blood that you have donated or that has been collected from you. Probably you want to tap out plasma from blood cells. You know, you can use physical methods like that to separate a mixture. So other examples of mixture, talking about air, just like definition of air is a mixture of gases. You know, you have your carbon dioxide, you have your nitrogen, you have your oxygen and the likes. All right, so let's go back to the options we have here. So if you look at common salt, sand, and washing soda, these are compounds, okay? They are chemically combined together. Common salt contains sodium and chlorine, okay? So that's why you have sodium chloride for your common salt. You know, you're talking about sand, I'm looking at silicon and oxygen. You're talking about washing soda, you know, that is Na2CO3 for the chemical formula. So which of the following is an example of a mixture? Blood is a very good example of a mixture. So the correct option here is option B. Question 2. Calculate the percentage by mass of nitrogen in calcium triazonitrate 5. Okay, so this is a compound with the old name calcium nitrate. All right, so it has this chemical formula. So what can we do? We can actually find the relative molecular mass of this compound by adding the individual relative atomic mass. All right, so we know calcium is 40, right? Just one atom of it. Okay, then look at nitrogen. We have one atom in the bracket here, in the parentheses here. Then you see this, we have 2. So 2 atoms of nitrogen will be present. So that will be 2 times 14 for nitrogen. Added 2, we have 3 atoms of nitrogen here, times 2, that accounts for 6, right, times 16. So I should have 40 plus 28 plus 96. Okay, so if I sum this up, I should have 164. All right, so this is what we have as a relative molecular mass. So how do we find the percentage by mass of nitrogen in this compound? So we know that nitrogen in this compound is actually how many? We have 2 atoms of it. So 2 atoms of nitrogen, right, over the total, this is 164, right, times 100 over 1. So what can I do? I can still try and do some breakdown, right? 2 here 1, 2 here, that should be 82. Yeah, very correct. 2 here 7, 2 right there should give me, I think, 41. Yeah, so I should have 7 times 100, I should have 700 over 41. If I divide this, I should have somewhat around 17.073. Yeah, thereabouts. If I want to bring it down, so I should have 17.1%. Okay, so maybe to 1 decimal place. So let's see if I have something around this. Okay, 17.1% of this. Okay, in the options provided. Yeah, very well, I can find that in option C. So option C is the correct option. Question 3. The droplet of water observed around a bottle of milk taken out of the refrigerator is due to the fact that the what? Okay, so what actually happens? Now, you should know this, that in the air, we have water vapor in heat. Okay, so what happens that you now see some droplet of water around this milk bottle, okay, taken out of the refrigerator, is because the air in the surrounding, okay, once it comes closer to the bottle, okay, of the milk, all right, so it slows down. All right, so the bottle of the milk coming out of the refrigerator produces a kind of cooling effect on the air, and it is the water vapor in the air that now begins to condense. Okay, so that is condensation. All right, you can see this too happening in nature as well. Okay, very close to what we can describe as the cloud, and that turns to rain, and then you can also see this so many instances. All right, so basically this is what happens. Okay, the water vapor in the air around the bottle loses some of its energy to the bottle. Okay, so and that is where you now see the droplet of water. So you should know that this droplet of water is not because the bottle of milk is leaking. No, not just that. It's the air from the surrounding that gets cooler, okay, when it comes in contact with the bottle of the milk. Or you can just say the bottle of the milk coming out of the refrigerator actually produces a kind of cooling effect. It cools the air around it. Then you see these droplets. At least I'm trying to relate this in a layman language. So take it that way. So we have option D as the correct option. Question 4. The volume of a given gas is V centimeter cube. Okay, then we have the pressure as P millimeter mercury. All right, so what is the volume? What is the new volume of the gas if the pressure is reduced to half at constant temperature? You know, you've seen that temperature is constant. This is definitely a description of Boyle's law. So you can recall that Boyle's law states that the volume of a given mass of gas, or a fixed mass of gas, right, is inversely proportional to the pressure. Okay, provided that temperature remains constant. Whichever way you want to take it, pressure or volume first. All right, so this is what we are looking at. So this is Boyle's law. So you recall this: P1 V1 equals to P2 V2. So let's sort out our given data. All right, so I should have my P1 as P, right, millimeter mercury. Then I should have my V1, my volume is given as V centimeter cube, right? Then my P2, we are told that the pressure is reduced by half, that is P over 2, isn't it? Then we now have this V2 is unknown. That is what we are looking for. So that means we are going to make V2 the subject of the formula right here. So what can I do? I have to divide both sides by P2, right? So that means my V2 equals to P1 V1 over P2. So if you try it out, this is how the derivation came up. So you can see it. So V2, then this. All right, so let's slot it in. Then I should have my P1 is P, right, times my V1 is V, right, divided by, isn't it? Then I have my P2. My P2 is P over 2. So that is P over 2. So that is what we have here. Okay, so let me just bring this down here. All right, so I have P over 1, right, times V over 1. Now if I want to convert this to times, it's going to be times 2 over P, remember. All right, so this cancels this, then I have 2V. So that means my V2 is actually 2V if the pressure is reduced, okay, is reduced to half rather. So this is what I have. So my V2 is going to be 2 times the initial volume. So let's go back to the screen to see if we can find 2V. Of course, with the units, you know, volume as a unit, centimeter cube, area, centimeter square, length, just centimeter. So option B is the correct option. 5. So moving from left to right across a period, the general rise in the first ionization energy can be attributed to what? Can be attributed to the increase in nuclear charge. All right, so first you should know that the first ionization energy, okay, you were talking about that amount of energy required to remove 1 electron from each atom, right, in 1 mole of a gaseous atom, okay, so that you can get a gaseous ion, so you can get as well 1 mole of a gaseous ion, okay, and we're talking about positive energy as well. You know, you have to talk about factors, some factors like distance between the nucleus and the outermost electron. You're talking about screening effect, talking about the size of that particular charge, okay, charged atom. So basically moving from left to right across the period, the ionization energy, the first ionization energy increases, okay, because there's an increase in nuclear charge, and down the group it decreases. All right, so the correct option here is option B, the increase in nuclear charge. Question 6. How many unpaired electrons are there in the nitrogen sublevels? So we're talking about nitrogen, okay, with atomic number what? So you can count with me: hydrogen, helium, lithium, beryllium, okay, boron, carbon, nitrogen, okay, that accounts for number 7. So it has this configuration: 1s2, 2s2, 2p3. So, and you know, when you are filling this these energy levels, okay, these sub energy levels, you know, you go first, then you now come back to make it face down. So the unpaired electrons that we have here, they are just 3. You know, that 2p3, that p orbital. So the correct option here is option A, 4, 3. 7. The stability of the noble gases is due to the fact that they what? Okay, so when you talk about noble gases, we can refer to them as rare gases or inert gases. They belong to the group 0 or the group O, all right, or if you want to say group 8, all right, of the periodic table. Okay, so we should know that they have no bonding electron, not no electron, okay, no bonding electron in their atomos shell. So this is cancelled because they omitted the keyword bonding. Okay, so now the stability of these noble gases is actually due to the fact that, you know, their stability or their own reactivity is due to the fact that their all energy levels where you can find electrons in their atoms, okay, is completely filled. So that implies that they have satisfied the duplet or octet electron configurations. Okay, so of course we know that they belong to group 0 of the periodic table because of this, because their atomos shell is filled already. So there's no chances for bonding to occur. All right, so if that's going to occur, then we are talking about other conditions, other setup entirely. Okay, but sticking with what I have here, so the stability of the noble gases is due to the fact that they have the duplet or octet electron configuration. Then we have examples. You know, we talk about your neon, we talk about your helium, we talk about your argon, we talk about so many like that. All right, so the correct option here, according to the context of the question given us, is option B. 8. The maximum number of electrons in the L shell of an atom is what? Okay, so you should know that this shell, they are actually numbered. Okay, we have you know, you talk about principal quantum number, that is n. All right, so the first orbit we're talking about n equals to 1, next orbit n equals to 2, next orbit 3, 4, like that. So the first orbit we're talking about the K shell followed by the L shell, right? M, N, O, P. All right, so you can see that. So to determine the maximum number of electrons that can actually fit in, or that a particular shell can consist, or that it can contain. So you know, the L shell is the number 2, the K is the number 1. So that means n equals to number 2. So the formula is 2n squared. All right, so if n is 2, since we are talking about the second orbit, that is 2. So that is 2n2, right? So I have 2, I have n, then I have 2. All right, 2n squared, rather, 2n squared. So if that is the case, now take note of this. So that means the n shell is 2, right? So that is 2 raised to power 2, that is 4. So 4 times this 2, that is 8. So the maximum number of electrons that can actually fit into the L shell is 8. So option B is the correct option. Number 9. So elements in the same period in the periodic table have the same what? Okay, so when you talk about period, you're talking about the same number of shells. Okay, so that is the correct option. If you look at atomic number, well, how do you say elements in the same period have the same atomic number? So how do elements share the same atomic number? We're talking about a different concept, a different phenomenon entirely for same atomic number. Okay, so when you look at chemical properties, okay, chemical properties that is same, okay, for some elements is because they are in the same group, and that is based on the fact that they have the same valence electrons. Okay, so physical properties, all right, when you're talking about physical properties, even when you consider a particular group, the physical property will change, all right, because there is increase in the atomic, whatever, the atomic makeup. Okay, so the correct option here is option A, for number of shell. Elements in the same period in the periodic table have the same number of shells. For group, same number of valence electrons. So option A is the option we are looking for. Right there, you can click on the link in the description below. It's going to take you to the Myschool website. Okay, right there, you get to download the Myschool mobile app, or you can get the Myschool software for your laptops. Okay, so why not try that out right now so that you can have a JAMB CBT experience to better prepare you for your coming exams. So let's solve question 10. So we have this equation. This is deuterium, this is tritium. So okay, so you can see this is helium, of course. Then we are talking about energy and radiation. Okay, so the reaction above illustrates what? This is hydrogen or fusion bomb for a nuclear fusion. So for a nuclear fusion, you are talking about the coming together of two light nuclei or two light nucleus. Okay, so nucleus is the plural of nucleus. That's why I use nuclei. All right, so they come together to form a single heavier nucleus. All right, with the release of energy and radiation. So this is a very good expression for a nuclear fission. Typically, or accurately, or to specifically, this is for hydrogen bomb, okay, or hydrogen or fusion bomb, how do you want to call it? So for nuclear fission, right, we are talking about the splitting of a heavy, unstable nucleus, all right, to give you daughter nuclei, all right, with the release of energy as well. So you are looking at this reaction. This is for nuclear fission. When you talk about alpha decay, you are looking at this kind of particle, helium particle. So let's stick to what we are working around with here. So you are looking at this and this to give you this. So this is for nuclear fusion. So option C is the correct option. At this point, we really need you to hit that like button. Also click on the subscribe button and always tap on bell notification so you can get alerts immediately we upload the next video content just for you. So we have question 11. A noble gas with a high power of fog penetration used in aerodrome beacons is what? All right, so at first let's take this, let's break it down. Now, an aerodrome, okay, or you can say an aerodrome, A-I-R, okay, aerodrome. You know, you are talking about that particular place whereby flights for aircraft take place. So when you now say an aerodrome beacon, okay, you are talking about that particular light that indicates the location of that aerodrome. All right, so we get that now. So we're now looking at what noble gas, okay, has this high power to penetrate fog. Okay, in case there is fog, you know, on a regular day there should be the penetrating power of that noble gas, even like 50 miles, okay, far apart, you should be able to see or indicate that, oh, there's an airport around. Okay, so we can refer to the aerodrome beacon as rotating beacon or aeronautical beacon. All right, so just to give you some edge, okay, about what we are talking about. So let's look at some of these noble gases. So at first I have krypton. All right, so there should be a Y here. So when we talk about krypton, okay, krypton alongside with xenon, you know, you can talk about them used to provide lightning, okay, or indication along these airport runways. Okay, take note of that. Krypton itself, you know, we are talking about the usage when it comes to fluorescent lamp, the stroboscopic effect. So when you talk about argon, you know, you're using argon to provide a kind of inert atmosphere when it comes to welding amidst many other usages. So when we come to helium, you know, because of its density, okay, it's low density, you can use it when it comes to filling of balloons, okay, for specific purposes. Then let's come to neon. Okay, neon is perfect for neon signs. Okay, but for this particular kind of setup, okay, the noble gas that I'll be going for is neon. All right, so I know we have one or two controversies about this, but based on the researches I've made, I'm going to go for neon. So the option that I will fall back to is neon. So option D is what I've chosen. 12. Permanent hardness of water can be removed by what process? Okay, so at first we have to know about temporary hardness and permanent hardness. Okay, so temporary hardness is actually caused by the presence of dissolved calcium hydrogen triazocarbonate 4. All right, so and we can remove that by boiling and by hardening slaked lime. All right, so when it comes to permanent hardness, it's actually caused by the presence of calcium and magnesium ion in this form of soluble tetraoxosulfate 6 and chloride. Very well. So how do we remove permanent hardness. Okay, we can use washing soda, we can use slaked lime, we can talk about pegmatite. So the correct option here will be option C, okay, addition or hardened caustic soda, NaOH. So option C is the correct option. 13. So substances employed as drying agents are usually what? Okay, they are usually hygroscopic or deliquescent in nature. All right, so you can also refer to these drying agents in the laboratory as desiccants. Okay, they are using desiccators. You know, they have very strong affinity for moisture, or you're talking about water. All right, so we can actually grade drying agent based on these three factors. We talk about capacity, talk about efficiency, and another property entirely. So let me just stick with what we have here right now. So I'm looking at the substance employed as drying agents are usually hygroscopic or deliquescent. So when we talk about deliquescent, we are talking about substances, okay, whereby when they are exposed, what they do is that they absorb water from the atmosphere, or they absorb moisture from the atmosphere, and they form a solution. All right, so when you talk about hygroscopic, you know, if they are solid, once you expose them to the atmosphere, they will absorb water. But if they are solid, they will just become sticky. No solution is formed. So when you talk about efflorescence, you know, efflorescence means when you expose a particular salt, okay, it loses its water of crystallization, either all or part. That is for efflorescence. So examples of drying agents in the laboratory, we can talk about your Conc-H2SO4, your fused calcium chloride, your silica gel, you know, that particular small white bag that you can find in your bags, in your shoes when you buy them newly. Okay, this is because that silica gel actually absorbs moisture from your leather material or from your shoes, from your bag, to avoid moisture, okay, causing it to smell or have stink or even to get spoiled. All right, so let's come back to option A, amphoteric. Amphoterism or amphoteric substances, you know, these are substances that can react as both acids or bases. Okay, so example like the oxide of your zinc, of your aluminum. So let me come back to acidic, you know, acidic property. All right, so we are talking about the ability to turn blue litmus paper red and other properties as well. So substances employed as drying agents are usually hygroscopic or deliquescent in nature. So option B is the correct option. Question 14. So calculate the solubility in mole per dm cube of 40 grams of CuSO4, okay, dissolved in 100 grams of water at 120 degrees Celsius. Okay, so we are giving the relative atomic mass of copper 64, sulfur 32, then oxygen as 16, that is copper tetraoxosulfate 6. So let me point that out. So I have to calculate the RMM, relative molecular mass, of this compound. So I know this is 64, added 2, this is 32, added 2. You know, I have 4 atoms of oxygen, that is 4 times 16. So I should have 64 added to 32, right? Added to 64. 4 times 16, that is 64. So if I add up 64 plus 64, that is 128, plus 32, that is 160. So normally I should know that 1 mole of this compound, we are talking about this, right, equals 160. Therefore, from what we are told that 40 grams. Okay, so X mole of this same compound will give us 40, isn't it? So let me cross multiply. So I will have this 40 times 1, isn't it? 40 times 1 equals X times 60 times 160 rather. So dividing both sides by 160, okay, 0 cancels 0. 4 here 1, 4 here 4. So I know that 1 divided by 4 is 0.25. Okay, if you want me to prove that, I can happily do that. So I have 4, I have 1. 4 in 1, okay, that's not possible, so I borrow 0. So 0 comes here. 4 in 10, it goes 2 times, right? 4 times 2, I have 8. So 10 minus 8, I have 2. I drop down 0. 4 in 20, that is 5. 4 times 5, I have 20. Okay, that's 0. Okay, we see that. So that's how I got 0.25 mole. So for 40 grams of this particular compound, I have 0.25 mole. So I've gotten the mole. So remember that your concentration in mole per dm cube, your solubility in mole per dm cube, we are talking about the mole over volume. So right now, I'm not told that the amount of water that we have is 100. So normally we should know that what we should have as 1 dm cube is actually 1000. So if I have 100, that's actually 100 over 1000, isn't it? 0 cancels 0, 0 cancels 0. So I have 1 over 10. So if you recall the formula I've just shared with you, so the solubility we are talking about here. So from the question, let me take the question again. Calculate the solubility in mole per dm cube. So the solubility in mole per dm cube. So let me just give you the hint. Mole per means over or divided by dm cube, right? So the mole is 0.25, okay? The dm cube is 0.1 dm cube, right? Okay, so that is 0.1. So 0.25 divided by 0.1. That is very easy for me. You know, I determined that this 0.5 is actually gotten from 1 over 4. I'm just trying to see how we can work without a calculator right here. So that is 1 over 4, right, which is your 0.25 divided by this 0.1. You know, we got our 0.1 from 1 over 10. So that is divided by 1 over 10. So that accounts for 1 over 4 times 10 over 1. So I have at the end of the day, I have 10 over 4. So 10 divided by 4 is actually 2.5. You can as well try this method to get your answer. So solubility in mole per dm cube is actually 2.5 mole per dm cube. So let's go back to the screen and see if we can find 2.5. Okay, for the solubility. Yeah, we have 2.50, of course. So the correct option here is option B for 2.50. 15. So coffee stains can be best removed by what? Okay, by a solution of borax in water. You know, this borax, we're talking about sodium borate or sodium tetraborate. Okay, so this is a very important ingredient when it comes to detergent and several other usage. Okay, so in this particular solution, this is what you should be looking for. So let's talk about the other options that we have. We are looking at the kerosene. Okay, for kerosene, you know, you can use kerosene to okay, in modern jet engines, as well as for lightning, you know, domestic fuel and the rest. Okay, so let's come to turpentine. You know, turpentine is important in paint. Okay, so that this paint material, let me just say in simple terms, let me just say for paint thinners. Okay, so that the paint can actually penetrate and bond with materials like wooden materials. Then if we come to ammonia solution, you know, out of several usage of ammonia, you know, I'm looking at ammonia for, it can be used in laundries, okay, as solvent for removing grease and oil stains. So I'm talking about coffee stains here. So what works best should be your option C for a solution of borax in water, because this dissolves in water very well. 16. Carbon 2 oxide, or you can refer to it as carbon monoxide, CO for its chemical formula. So it's considered dangerous if inhaled, mainly because at first you should know this, you know, it's a colorless, odorless, tasteless gas that is slightly less dense than air. Okay, so the reason why it is considered dangerous is because as little as 0.5% of it in air, it can actually lead to death. Why? Because it competes with the oxygen in the blood. All right, so it attaches itself or combines with the hemoglobin in the blood that actually transports oxygen, and the hemoglobin is now converted to carboxyl hemoglobin. So that cannot transport oxygen. And you know, when there is lack of oxygen, it leads to death, okay, of those vital organs in the body. You know, oxygen cannot be transported, you know, starting with the brain. All right, so the main reason why it is considered dangerous is because it competes with oxygen in the blood. And this carbon 2 oxide or carbon monoxide is actually produced, okay, when there's an incomplete combustion of carbon compounds like your gasoline. So the correct option is option B. 17. So the acid that is used to remove rust is what? So let me just clear up the ones that we don't need. Okay, so boric acid, that's a very good, it's good for pesticides. Okay, so let me come to triazonitrate 5, okay, for rocket fuel. Okay, then let's come to hydrochloric and tetrazosulfate 6 acids. All right, so you can refer to this as muriatic acid. this as sulfuric acid. Now, the truth is that both acids, they are actually useful when it comes to pickling of metal before electroplating or before galvanization. All right, so pickling means that you want to remove rust, okay, especially from iron before you electroplate. Okay, you are just like a cleansing process. Okay, how do you just go about the pickling? You just take that particular metal, especially this is very useful in steel industry. Yeah, so you take that particular metal after you are done with most of the processes. Okay, so then you dip it into the pickle liquid. That can be this or this. All right, so what happens right here is that the metallic oxide, okay, on the surface of the rust, let me just say rust, the rust available on the surface of that particular metal, like iron, okay, is being removed by this process. Now the thing is that modern times now, what we use is this hydrochloric acid. Why? It is faster. All right, although this was what has been in use before now, but this is faster, and also this minimizes the loss of the base metal. Okay, so that means it's not going to eat up or eat away the metal as much as this does, sulfuric acid does. Okay, so that is why we go for hydrochloric acid. So take notes, this is my emphasis. Tetraazosulfate 6 acid, hydrochloric acid, they are used for pickling, okay, to remove rust, okay, in the steel industry. Remember that steel talks about the combo of iron and carbon. So this is very useful in steel industry, talking about electroplating and galvanizing. We can use this, we can use this, but for effectiveness or for efficiency, okay, this is faster and it minimizes the loss of the base metal or the parent metal. So the correct option or the most valid option is option B for hydrochloric acid. Question 18. So calculate the volume of 0.5 mole per dm cube of H2SO4, okay, that is neutralized by 25 cm cube of 0.1 mole per dm cube of sodium hydroxide. That's your caustic soda. Okay, so this reminds me of titration. You know, you use your pipette, your burette, and the likes. Okay, and your funnel. All right, so this is the formula. Okay, when it comes to this, so CAV over CBVB equals Na over Nb equal Na over Nb rather. So Ca, concentration of the acid, volume of the acid, concentration of the base, volume of the base, number of moles of acid, number of moles of base. Let's write out the equation of reaction. So I have the acid, right? It reacts with the base. Okay, so strong acid, strong base. So I have this. This should be my product, right? So remember your neutralization reaction. Okay, what you should have is salt and water. So this is salt and this is water, of course. So this equation is not balanced. Okay, so I can balance it by putting 2 here to indicate 2 moles of the base. Okay, so if you look at it now, it should be balanced by now. So 2 moles of water we have. Okay, the same thing here. We have 2 of this. We have 2 atoms here. Okay, oxygen is 2 here. Here we have 2, making 4 in total. That is accounted for. So we can see that the number of moles for the acid is 1. Number of moles for the base is actually 2, right? Concentration of the acid from the question, we are given 0.5 mole per dm cube. Concentration of the base, okay, we are given 0.1. All right, volume of the base, we have 25. Okay, so let me slot this in. So what we have to find is the volume of the acid, VA, that is unknown. So if I'm asked to find VA, what can I do? I'll just make VA the subject of the formula. Okay, so doing that, let me just work with this. That'll be VA, right, equals CB VB, right, times NA over CANB. All right, so let me just work with this. So I have my VA equals the CB, concentration of the base, that's 0.1, or I prefer to use 1/10 because I like to work without calculator right here on this platform. So this is 1/10, still means 0.1, please. So you can just punch your calculator. All right, so I have 1/10 times my VB, volume of my base, that is 25/1, right, times my Na, number of moles of the acid, that is 1, right, over 1, divided by, Okay, so what do I have? I have the concentration of the acid, that is 0.5. 0.5 is 5 over 10 or 1 over 2 if you simplify. So I have 1 over 2, right, times the number of moles of the base, that is 2 over 1, right? So this cancels this. So at the end of the day, I have 1 right here. So that means for the base, this is gone, okay? So 1 times 1, that is 1. 1 times 1, 1. 1 divided by 1, that is 1. So I just have this. I'm left with this, right? This is gone. So what can go here? I can just say, okay, 25 times 1, that is 25, times 1, that is still 25, okay? Then I have 10 times 1, that is 10 times 1, that is 10. So 25 divided by 10, that is 2.5. Or I can even decide to break it down by saying 5 here 5, 5 here 2. 5 divided by 2 is to give you 2.5. Remember your units. Okay, so let's see if we have 2.5 in the options provided. Very well, we have 2.5 cm cube. Okay, the volume we are using, it has the units of cm cube, not the m cube. So the correct option is option B for 2.5 cm cube. Number 19, so the color of methyl orange in alkaline medium is what? Okay, take note of this. You know, we're talking about a pH of 3.1 to 4.6, ordinarily for methyl orange. So we're talking about orange color. Okay, so when it's in an acidic medium, what you should have is red color. All right. In an alkaline medium, okay, we are looking at your yellow color. All right, so the correct option here is option A for yellow. So I'm pleased to inform you that it is stress-free for you to be able to ask your questions right now. So all you just need to do is to click on the link in the description below. It's going to get you to the Myschool website. So right there you get to meet with our solution providers after you ask your questions. So join me as we solve question 20. So which of the following salts is slightly soluble in water? Alright, so if we look at silver chloride and lead chloride, okay, these guys are actually insoluble in water, though this is soluble in hot water. Okay, so then we have this calcium tetrasulfate, 6 salts. Now this salt is slightly soluble in water, so this fits the description we are looking for. Now coming to this, okay, your washing soda. Alright, the carbonate of sodium, of potassium, of ammonium, they are soluble in water. All right, so what we are looking for is found in option B. So option B is the correct option. So it is very possible that you have better steps or explanations that you would like to share. Please, we are so much attentive. All you just need to do is to use the comment section below and indicate the question number and the explanations or solutions you like to recommend. Number 21, so in the above reaction, the reducing agent is actually this. Okay, this is it here, phosphorus 3-hydride. Okay, so phosphorus 3-hydride and diphosphine, these are the hydrides of phosphorus, all right? And this, of course, is a strong reducing agent when it comes to this reaction. So you can say that it actually brought it to the metals or the phosphides. All right, so as well, if you look at certain properties of reducing agents, you know they are very good electron donors. So if you observe this, you should be able to see the increase in the oxidation state as well. All right, so the correct option is option C for phosphorus 3-hydride. 22. So the IUPAC nomenclature of the compound that we have here is what? Okay, so at first this compound is actually gotten, you know, when you talk about the reaction between aluminum chloride, all right, and lithium hydride, and this should be in excess so that you can get this particular compound. So the IUPAC nomenclature, the name for it, the proper name for it is lithium tetrahydroaluminate 3. So where do we have that? So I think I can find that in option A, looking carefully, lithium tetrahydroaluminate 3. So that is the IUPAC nomenclature for this compound. So option A is the correct option. Question number 23. So iron can be protected from corrosion by coating the surface with what? Okay, at first, so let's talk about corrosion of iron. Corrosion of iron is actually referred to as rusting. So what is rust? You know, rusting actually occurs from the action, or corrosion occurs from the action of atmospheric oxygen and water. So this is where you now have your brown hydrated iron 3 oxide. Okay, so for that reason, so how do we now prevent rusting? Okay, so there are ways we can use. We can use paints and tars. We can use grease and oil. We can use the galvanization method. Okay, that is the use of zinc. Okay, but if you look at copper, silver, and gold, as well as chromium, okay, you can actually use them as well to coat the surface of iron in the process referred to as electroplating. So electroplating is unique to these three, but the one that actually stands out, that is zinc. So galvanization. So because of the distinct nature of how zinc actually is stood in these options, so I think I will just go for zinc. So zinc is the viable option. 24. So what quantity of aluminium is deposited when a current of 10 amperes, okay, is passed through a solution of aluminium salt for 1930 seconds? So I'll be solving this question based on the laws of Faraday's laws. Okay, so I'm basically going to work on the second law. All right, so just take note of this. Recall that, you know, one coulomb of charge when you're talking about a univalent ion, right? So, and that is 96500. So another aluminium is trivalent. You know, aluminium, if you want to write the charge, that is 3. So that means I'm going to require 3 times this, isn't it? Okay, to produce the regular atomic mass, okay, of aluminium. Relative atomic mass of aluminium is 27, isn't it? So right here, I'm now told that for this amount of current, that is 10, right, times the time it actually passed through the salt. Okay, so we are told that when a current of 10 amperes is passed through a solution of an aluminium salt for this time frame. So you can see what I have here. So how much or what is the quantity is going to deposit, that is unknown, of course. So that is what we are going to do right there. So if I cross multiply, then now we have x equals, right, equals 10 times 930 times 27, right, over this 3 times 9, 6, 500. Okay, so 0 can pull out 0, 0 can cancel 0. Okay, so what more can we still address? Yeah, I have this goes here 1, this goes here 5 times. Okay, very well, then I still have 3 here 1, 3 here 9. So for the numerator, I have 9. For the denominator, I have 5. So 9 divided by 5 should be 1.8. If you would like to go through this with me again. So 5 in 9, that goes once, that is 5. 9 minus 5, that is 4. I know this cannot pass through at 0. 5 in 40, that is 8. That is 40 minus 40, my remainder becomes 0. So you can see we're talking about 1.8 grams. So let's see if we have this option provided. Okay, so I can find that in option B, so option B is the correct option. Question 25. So in which of the following is the entropy change positive? Now take note of this. If it is absorbed, okay, entropy change is positive, okay, because there's that means the reaction is spontaneous, and we can't talk about this without talking about thermodynamics. Okay, so thermodynamics is actually talking about the relationship between it and every other forms of energy. So we have the first law and the second law of thermodynamics. So the first law talks about that energy can neither be created nor destroyed, but it may be converted from one form to the other. So now under the second law, after considering factors, okay, we now have 2 significant ones, or 2 that I can talk about. We talk about the free energy and the entropy change, or the entropy. All right, so this entropy right now is talking about the measure of the degree of disorderliness or random movements, okay, in a particular reaction. All right, so coming back to the second law of thermodynamics, it said for a reaction to be spontaneous, okay, there must be increase in this. All right, so having established that, so in which of the following is the entropy change positive? That means energy is absorbed and there's an increase in this value. Okay, so in such case, what we are looking at is this thermal dissociation of ammonium chloride. All right, or you can look at the thermal decomposition of calcium triisobicarbonate 4. Now, reaction between an acid and a base, that's neutralization reaction. Addition of concentrated acid to water. Okay, the solution of sodium metal and sodium metal in metal. You know, when I talk about B and D, we are talking about exothermic reaction, because if you just add this to water, you know, it reacts violently. There's release of energy, exothermic. Okay, so as well as this, okay, addition of concentrated acid to water. So you can see, that's why you are told in the lab that, oh, when you are walking around reagent, okay, is it that you had acid to water, you had water to acid, okay, because of the dangers attached to that kind of experiment. So the correct option here is the thermal dissociation of ammonium chloride. Right there, we've come to the end of this video segment, but there's so much more to come. All you just need to do is to please hit that like button, also click on the subscribe button, and always hit on the notification so you can get alerts immediately we upload the next video lesson just for you.